So, and our next speaker is Giovanna, and she will speak about a better approximation for interleaved Dyck reachability.
Hi everyone. My name is Giovanna, and I'm going to be presenting a better approximation for Interleaved Dyck Reachability, which is a work I did with Andreas Pavlogiannis. So first of all, let's talk about what Interleaved Dyck Reachability is and why do we care about it for static analysis. And here we're going to be trying to solve a very simple problem, which is if the value of a variable A can flow into another variable C in a program. That's very simple. You can imagine all the applications that this can have in all these different types of static analysis. We're going to be focusing on like one specific set of benchmarks here just to exemplify our tests. And we're going to be testing on a taint analysis benchmark on Android. So essentially seeing if you taint a variable. So if there's a flow from some sensitive data, such as your phone's location, to somewhere you don't want it to be, like an untrusted sync, a log to an app that might be malicious. So, how do we solve a problem of if a variable can flow into another one? If we look at this little program here, right? An intuitive thing is to create a graph. So we add an edge between two variables. So here A goes into B. We add an edge from A to B. And now we only need to check if A reaches C. If A reaches C, then the value of A goes to the value of C. And this is very cool, but it kind of gets a little bit more messy once we have more complex programs. If we have function calls, so let's say something like this, right? And we have that the value of A flows into B, because A goes into this next X is going to be next A, return A plus 1 goes into B. But if we do the graph here, like we described before, well, A reaches B, which is nice, but also C reaches B, because C goes into next. We have next of C, return C plus 1, and we have the return here. And we don't want to identify these types of paths. So one way to deal with this is to put parentheses. So whenever we call a function, we add a parenthesis corresponding to the call site. And when we return, we must return where we came from. And now all the valid paths here are well-nested paths in parentheses. So like A from B is well-nested, but C from B is not well-nested anymore because the labels of the parentheses don't match. And we have a similar thing when we're talking about compositive data types. So here, for example, I have that A flows into the X field of P, and then the X field of P goes into C, so A reaches C. But through the Y field of P, B also reaches C. And we need to handle this using this time brackets, so we differentiate them. And the path needs to be well-nested for us to have a valid relation here. Awesome. What about if we have, oh, okay. So how do we check if a path is well-nested, actually? Well, well-nested parenthesis is what we call a Dyck language, which is a context-free language, which means it can be written this way. And when we're talking about finding all the pairs in a graph that have a path that belongs to a certain context-free language, this we can do in O of n squared, and this is good for us. Let's be happy about it. Okay, but now what if we want to handle both context and field sensitivity simultaneously? Things get a little bit hairy here. So we have this program that has both. And I'm not going to go into this example very much, but essentially we want to find a path here from A to C that looks something like this. If I take this path and I write the labels and I squint and I only look at the parentheses, this is well nested. And if I squint another way and I only look at the brackets, that's also well nested. So this language is called Interleaved Dyck language, which is the interleaving of two Dyck languages. And finding interleaved Dyck reachability is actually undecidable. So we cannot solve this problem ever. There's no algorithm. There never will be. So let's seek to overapproximate the number of reachable pairs. First of all, I'm going to talk about some current approaches, and then I'm going to talk about how we improved on them. The first thing you may think of is intersection. I said that if we squint one way and you only see parentheses, it should be valid. And if we only see brackets, it should be valid. So let's do this. If I want to see if A reaches I, I'm going to check if there's a path valid from A to I in parentheses, ignoring all brackets, and a path that's valid, ignoring all parentheses. If it's valid on both, then I say that A reaches I, and I'm happy. Of course, this doesn't solve the problem because it can't. So we can have a problem like this, right? Here the path from A to E that's valid on parentheses is different than the path from A to E that's valid on brackets. But our algorithm is going to say that A reaches E, even though there's no path that is reachable on both at the same time. So what we're going to do here is we're going to run these algorithms, and each of them is going to present us with an overapproximation, and I'm going to be plotting the number of potential false positives. It's potential because I'm comparing it with underapproximation, because we don't have the exact number, because undecidable. So this is what it's going to look like. I have all these benchmarks, and these are the potential false positives normalized by worst method. Why are they all the same length? It's because this is always the worst method. Out of the methods we're going to compare. It's kind of the naive approach. Then now let's talk about our first real algorithm, which is the mutual refinement, which was proposed by Schrödinger and Kirun-Zhang last year. And this works by iteratively simplifying the graph. If we look at this graph here, we have this closed parenthesis 3. But we don't have an open parenthesis 3. This means that this edge is never going to be part of a valid path, right? So we can just remove it from the graph. So we're going to essentially be doing this with both languages. We identify all the paths that are reachable through parentheses, and we eliminate the edges that are not in any of them. And we do the same for brackets. And now we get a new graph that has less edges. And then we do this again. And we do it until the graph that we start with is the same as the graph that we end with, i.e. it converges. In practice, this generally converges pretty fast. So it converges in around 3 to 5 iterations. And then once we converge, we run intersection on this final graph. Notice that this method is also not perfect. Let's look at this example here. The path from A to D is still misidentified. Here I don't remove any edges because these edges here on this upper path are all in a valid path from A to E, and the one in the lower are all in a valid path from A to H. But there's no valid path from A to D. But how does it perform compared to our previous intersection method? It's a significant improvement. Maybe half the paths here, half the potential false positives. So it's a decent improvement. Let's see how we can make that even better. The first thing we may think of is augmenting this context-free language, because we're essentially running two languages. One of them, we only look at the parentheses and we ignore the brackets, and the other one, we only look at the brackets and we ignore the parentheses. But this is wasting information. We could essentially add some information to the brackets that's easy to incorporate into a context-free language. And that would make the languages we're considering more refined. So let's look at this previous example of mutual refinement and try to come up with a reason on why A will never reach D. Kind of an easy excuse that we could just incorporate into a CFL. And an easy property of these Dyck languages we can exploit is that they're always even. When we add parentheses, we're adding 2 of them at a time. Since these paths all have odd length, they're never going to be valid interleaved Dyck paths, right? So we can just now, instead of our CFL identifying strings that the parentheses are well nested, we're going to identify strings that the parentheses are well nested and the number of bracket characters is even. And then we're going to run mutual refinement for this grammar and the bracket equivalent in which the brackets are well nested and the number of parentheses is even. Another thing we can do here in augmenting our CFL, let's look at this example now. This is an example where all the conditions I said so far fail. So our algorithm would say that B reaches D, even though it clearly doesn't. And an easy condition on why it clearly doesn't is because all the paths from B to D start with an open parenthesis or an open bracket. And when you think about a well-nested parenthesis, it always starts with an open parenthesis or open brackets, right? So we're going to augment our CFL again, and now add a condition for the parentheses that the first bracket must be an open bracket, and the last bracket must be a closed bracket, and vice versa for the bracket language. And we're going to run mutual refinement on this. These are all conditions that are pretty easy to add to our CFL. And how does this perform compared to our previous algorithms? Well, we remove another bunch of paths. You see, for many of them, we're extremely close to our underapproximation. And the last thing here we're going to be doing as an optimization is considering an on-demand setting. So let's look at this example here. Why do we not remove the bad edges from A to D? Well, because they are in a valid path from A to H, for example, or A to E. So if we only think about the edges and how they impact a valid path from A to D, then we will remove this open parenthesis here and this open bracket here. So we can run on demand for A to D if we really care about knowing if A thanks D or something like that. So we're going to query for a single potential reachable pairs. And then we use mutual refinement and exclude edges that are not in a path from the exact path that we're asking about. And how does this perform? Well, we can decrease a reasonable amount of more paths here around. So now let's talk about some additional considerations and what do we get from all this. First of all, runtime, which is something that you guys are probably asking about. So our grammar-augmented methods, they increase the CFL by a constant size. So it's going to be slower by a constant factor. And these grammars that we wrote, they're actually incremental, so you can choose to improve as many of the conditions as you want, and we actually have a generalization on one of these conditions. So essentially, for as much as you want, you can pay slowness and get like less reachable pairs. And the on-demand setting here, it increases precision if you're only talking about one pair. But of course, if I want to find all reachable pairs, I would have to run for all pairs. Not really, we can optimize that. But still, for all pairs, it's going to be much slower. But if I only want to know for one pair, it's going to be a little bit faster. So our overall results, essentially we designed stronger methods for overapproximating this interleaved Dyck reachability that improved on the previous best methods. And the number of potential false positives, which was purely 55%. So out of the paths that are reported, only these we know are actually reachable, and these ones we're not sure. Now it's going to be 12%. So we know that only these are the pairs that we don't know. And actually, kind of off the record, we know that these numbers are actually much better. We are working on better underapproximations, and we know that for these benchmarks that are showed, for at least half of them, we obtain an optimal answer, which means that for these benchmarks, we have the exact solution for this undecidable problem. But that's pretty much it. Thank you.
Thank you very much for your presentation. Are there questions? That's the first one.
Thanks, this looks super interesting. I was wondering, I'm not sure if I understood this right, but at some places it seemed to me that you would need to know already large parts of the graph ahead of time in order to determine what can be eliminated or not. Is that the case, or can you really do this all on the fly as you compute the graph?
No, we're doing like a static analysis, so we're kind of just getting the whole graph, the whole program graph as an input. So we get this whole thing as an input.
But that's not normally how people do things? Okay.
Sorry. Yes.
Yeah. I mean, that can sometimes be prohibitively expensive, right, if you want to build that up front.
Yeah. So I know at least for this Android benchmark, we're looking into like vulnerabilities. So they were trying to look like vulnerabilities in programs that execute certain simulations. So it would be something about, this method would be used to detect like big vulnerabilities on code. So you could justify like running a static analysis, and in practice this runs like in a couple of minutes. So it wouldn't be something that you were going to be running on your house whenever you code something, but more like a process to detect vulnerabilities.
All right, thanks.
You mentioned that one of the filtering methods is to check whether the length of paths is even. Could you also do that by checking that the length is checking the length modulo the number of interleaved languages?
What do you mean? Oh, yeah. So, you mean to generalize this for like more parentheses? Or
yeah, so if you have, I don't know, say 3 languages that are interleaved, it's still true that it has to be even.
Yeah.
But would it also have to be a multiple of 3, for example?
No, because I could always like add 2 of just parentheses, right? They don't have to have the same length. I could have like, 5 pairs of parentheses and 0 pairs of brackets, 6 pairs of parentheses and 1 pair of brackets. So the languages are kind of independent. They each have to be even simultaneously, and the addition of 3 even numbers, the only guarantee we have that is even. But we do, like, in actuality, we implement a slightly more general version of this in which we check the parity for, like, subsets of bracket types. So we can say, for example, that, like, the brackets of label 1, those have to be even, and if we only look at the brackets of label 2 or more, those also have to be even. And we can keep like the conditions for each of those subsets in our grammar.
Okay, thank you.
So coming back to Eric's question, there has been a lot of work on trying to scale static data flow analysis, especially for Android apps. And there are many papers out there that talk about the memory consumption of that. And we're talking about graphs that even if you prune unreachable call sites, so you have a call strings approach when you return to something that is an infeasible call leaf, or that you just drop it, you don't even put it in the graph. We're talking about graphs of 30 gigabytes or more. So we're not talking about such small graphs. So I really wonder whether it is feasible for large apps, and we're talking about things like the Facebook app, we're talking about the large banking apps and so on, to really make this an analysis once you have the full graph. Because as I said, there are many, many papers complaining about tens of gigabytes of those graphs, even if you prune early on and prune eager.
Yes, absolutely. Like, this is not gonna be able to run on something that is that large. The static analysis is already a compromise because running dynamic analyses on these types of applications is not feasible just because they are so large. And these methods, I mean, we're running here for like reasonably big applications, but I don't think they're necessarily scalable for something that's very huge, unless you let it run for like a very, very long time, which maybe if you're looking at like vulnerabilities for something as big as Facebook, they can afford the processing power or the size for it. But like, it's not, I think the point here was mostly to check like how good the overapproximations are and try to find like, where are these numbers? Because we know now that like these previous methods overreport a large number of paths, and we know how to get close to them. But I don't think something like this will be running on the back end of any companies very soon.
Okay. So any more questions? If not, then thank you again.